Good afternoon. So we are back here with lecture number 23 on this course on silicon and wide bandgap power devices. I'm Professor Ananta Agarwal at the Ohio State University, and I have here my colleague Dr. Arash Salami, who gave the last two lectures on processing of silicon carbide MOSFETs and the layout designs. And again, would like to acknowledge that this course is funded by Office of Naval Research. And today we will cover the topic of MOSFET switching transients and also the ruggedness of MOSFETs. So let's start with the switching transients. So this is a typical half cell of a DMOSFET we have been discussing, and we of course acknowledge the book by Professor Jayant Baliga listed here, from which we have borrowed this material. So in this half cell, we have the N plus source, P well, and the JFET region, which we have been talking about, and of course the N drift layer. Source is on the top, here is the gate, and the drain is at the bottom. So basically, if you look at various capacitance components, you have a capacitance between gate and source metal listed here as CSM. You have a capacitance between the gate and the N plus source listed here at C to N plus. Then CP is the parallel plate capacitance between gate and the P well, and then the gate drain capacitance, and of course the drain to source capacitance here. So the gate drain capacitance also is between gate, and actually there are two capacitances here. One is across the oxide, and then the other one is across this depleted portion of the semiconductor. So normally when we talk about capacitances, we talk about capacitances between gate and source, which is CGS, gate and drain, which is CGD, and then drain and source capacitances, CDS. So here you can easily identify that the gate drain capacitance is the capacitance here, which is the series combination of the oxide capacitance and the depletion capacitance in the N minus drift region. This contributes to gate to source capacitance. This is also gate to source capacitance, and this capacitance over the P well is actually divided up between gate source and gate drain, and then this is the CDS, drain to source capacitance. So in literature and in specification sheets, sometimes we list CISS, CRSS, and COSS, and I have given you the transformation between these values in terms of the gate drain and gate source capacitances, etc. But it's much more meaningful to think about gate drain, gate source, and drain source capacitances, and now you see where they are coming from within the structure. So now we are ready to discuss the turn on and turn off transistors, turn on and turn off transients of this transistor. And to do that, we have considered a simple circuit, again borrowed from Professor Baliga's book, So, this is the MOSFET we want to consider. Here is CGS, here is CGD. We have not shown you CDS, but it is here across the drain and source. And we have put an inductive load and a freewheeling diode across the load, and the total current that is flowing in this system is the total load current IL. And we have two switches here, schematically speaking. This is just a cartoon that when we close S1, we turn on the device, and when we close S2 and open S1, then we turn off the device. So, let us consider the turn on transistor. That means S2 is off and S1 is turned on. The gate voltage, which is VGS, an external gate driver, starts charging the gate source capacitance. So, there would be a current flowing which is a displacement current across this capacitance to charge up this capacitance up to the threshold voltage, and when this capacitance is charged up to threshold voltage, then we will start the transistor will start conducting and will charge the gate drain capacitance. So, initially we assume that all the load current is flowing across this freewheeling diode. So, this IL is circulating here, no current going through the drain, it is 0, and we turn on the transistor. So, basically the device is off, and when we apply high gate voltage, we turn on and we transition from T1 to T2, and then we transition from T2 to T3, and during this portion of time the device stays in the saturation region, and then from T3 to T4 we say that the transistor has entered the linear region. So, the total turn on transient from T1 to T4 is made up of several transitions, but the trajectory is shown here. This is the on state and this is the off state. Then during the turn off, we start from the turn on state and we go backwards the way we came, and now we end up in the off state. So, this is the approximate trajectory of what happens when we turn on and turn off, and in reality it is a little more complicated because that depends on the inductive load and things like that. So, for now let us think about specifics of the turn on transition. So, here we are plotting the gate transient, the drain current and the drain voltage. As I said, the drain is initially off, so the drain voltage is high, drain current is 0, and we turn on the gate voltage, and the gate voltage starts charging CGS and CGD so that it reaches the threshold voltage, and at that point the transistor starts turning on, and the current that was circulating through the diode now flows through the transistors, and at this point at time T2 all the diode current has transferred to the transistor, and at that point the transistor enters into what is called as Miller plateau. This is where we are charging CGT. So, the voltage stays constant, the total current through the transistor is constant, and the voltage across the drain is dropping because we are turning on the transistor. And CG at this point, CGD is basically charging up. Now, once we reach time t3, we can CGD is fully charged up. Now we can increase the gate voltage and we can start charging CGS again. So typical gate source voltage waveform would look like this. At the gate terminal, the drain current would look like this and the drain voltage would look like this. I would encourage you to read the notes on the left hand side. Stop the video at this point and read the notes and you will understand in detail what is happening. Now thinking about the turn off, we basically reverse our path. So gate voltage goes from on state to off state, which is below the threshold. Drain current goes from on to off, and the drain voltage goes from on, which is low value, to the off position. And again, I'll encourage you to read the notes on the left hand side, and that will essentially tell you what is going on. And again, this time between T4 to T5 is where the CGD is charging or discharging. So with that, let's move on. So here we have schematically shown a device in the on state. So the current is high, the voltage across the transistor is low, called the forward voltage, when the forward current IF is flowing. And then we turn off the transistor and it goes roughly like this. So what we have done is we have shown you this transition of the drain current from high to low right here, and then the transistor remains in off state. That means the current is small and the voltage is fully, the full voltage VR is across the transistor. And then at this point we start turning on the device again. So the gate voltage increases, the transistor current increases, and the drain voltage drops to some low value, which is the on state voltage. So this turn on we have schematically shown you here. The drain current increases from between T1 and T2, and drain voltage reduces between T2 and T3. So we have idealized that curve here just to simplify our analysis. So these are the same times we have mentioned in the previous slides: T1, T2, T3, T4, T5, T6. The total time period is capital T from off state to, from on state to off state back to the on state. So this capital T is the one full period of off state and on state. So now you can start looking at the losses. So first of all, in the on state we have what is called as conduction losses, and that's basically IF times VF. And since the transistor is only on for the amount of time T1, we define a constant delta, which is T1 divided by the total time period. So that means it is on for delta fraction of the time. So now we multiply the losses with delta to get the total conduction losses within one switching transient, off state and on state. Similarly, during the off state, the leakage current is very small and there is full voltage across the device. So, now that is the loss, that leakage current times the reverse voltage across the transistor, and that loss is only occurring for 1 minus delta of the time, that is only part of the time period capital T between T2 to T5 is what is sorry, T2 to T5 is what is going on, is the losses in the off state. And normally the leakage current is very small, of the order of microamps. Generally this off state loss is very small, but if the leakage current goes up, for example, you increase the temperature, then of course this loss becomes substantial. All right, then we have switching losses. The turn off switching losses are the losses that happen when we multiply current and voltage during the transition time, and that transition time is T1 to T3. So, we multiply the current times VRs. So, basically if you multiply these two waveforms, you will get a triangle. So, basically you will get a triangle of power which is like this, and the area of that triangle would be IF times VR divided by 2, and then we multiply it with the time period that this loss is taking place, that is T1 to T3, and then this is the loss once every cycle. So, if we multiply it by the switching frequency, that gives us the total turn off loss so, if the switching frequency is high, then so many cycles are taking place in every second. So, the loss becomes higher. Similarly, if the switching frequency is low, then the turn off loss is lower. The turn on loss is the same thing. This is where we are turning on the device again. So, turning on the device would be during time T4 to T6, and then we multiply the current and voltage during T4 to T6, and that gives us the turn on losses, and again we multiply by the frequency and divide by 2 because it is a area of the triangle, we get these losses. So, the total losses that are going on are steady state losses, which are called the conduction losses during on state and off state, and the switching losses, which are shown here, and these are called the turn off switching loss and the turn on switching loss, and they depend on the frequency, switching frequency of the device. All right. So, obviously, it is important to reduce the conduction losses, which is generally this loss, and it is generally good to try to reduce both of the switching losses in the device. So, now let us talk about the DVDT capability of this device. So, we have again borrowed this example from Professor Baliga's book shown here. So, basically we are turning off the device, that means the drain voltage is rapidly increasing. So, in this circuit we have shown a control chip that basically is your gate driver, there is a control FET, there is a power supply here, and here is the output voltage. So, the transistor that we are considering is shown here. drain, gate and source, and we have shown you the gate drain and the gate source capacitance, and we have not shown you the drain source capacitance in this figure. So, now the device is turning off and we want to figure out if the device will turn on by some means. So, if we look at two cases, first is the one shown with blue arrows, and we assume that this gate impedance is much higher than the impedance of the gate source capacitance. Then as we turn off the device, the blue arrows indicate how the displacement current is flowing through CGD and CGS. So, we are turning off the device, we are increasing the drain voltage at a rate of dV over dt, and we want to calculate. So, no current flowing through drain to source, but the displacement current shown by blue arrows will flow from through the gate drain and gate source capacitances. So, the voltage across this gate source capacitance, which is the gate voltage, is given by the ratio of CGD divided by CGD plus CGS times DVDT times time. So, that is how the voltage across the gate source is developing, and of course, if this gate voltage goes above the threshold voltage, then this device will turn on. We do not want it to turn on, and at a certain value of dVdt, this device will turn on because the gate voltage will rise above the threshold voltage. So, you can see that if we want to reduce, improve this dVdt capability of the device, how many volts per microsecond we can use to turn off this device depends on CGD, and if CGD is 0, then we have infinite dVdt capability. Then the other part is showing with the red, has been shown with the red arrows, where the gate driver impedance is less than CGS. Then the displacement current will flow as shown by red arrows. It will flow through CGD and will flow across the gate resistance. And again, you can calculate the gate voltage as a function of time, and that will depend on how fast the drain voltage is changing and the gate resistance in CGD. And you can see that if dVdt is very high, the gate voltage can rise above the threshold and the device will turn on. So, we do not want the device to turn on. That means we really need to reduce CGD to improve the dVdt capability of this MOSFET. And the dVdt capability is required because in power electronics we want to switch these devices very fast, and we do not want this device to turn on when we are turning it off in a very rapid manner. So, let us see what is going on inside the device as we increase the drain voltage very rapidly at a rate of dVdt by dt. You can see that there is a internal capacitance between drain to body, which is same as what we mentioned earlier, the drain source capacitance. Then as we increase the voltage on the drain, there is a displacement current that is flowing through this output capacitance CDS or CDB, as we have mentioned here, drain to body, body being the P well body. This current flows laterally through the resistance of the P well and then is collected by the source contact, right. So, if we increase DVDT, this amount of this current will rise, which means this point A will be will charge up to some higher voltage because of this drop across the resistance. And because of the drop across this resistance, point A will rise in voltage, and at some point this base emitter junction, we call it base emitter junction, that is a bipolar junction terminology, but it is really this N plus P junction that gets turned on, and when that junction gets turned on, then this parasitic BJT, which is NPN, is turned on, and the voltage cannot be supported between source and drain. So, essentially, in addition to the CGS and CGD charging, which I showed you in the previous slide, we also have to reduce this resistance in the P well, so that the device internally, through the output capacitance of the device, does not turn on the internal BJT. So, this is called the bipolar turn on, and it is very easy to avoid this problem by reducing the resistance of the P well, and that is why in many silicon transistors we dope this region very heavily. We do not want to dope the channel region very heavily because we have to form the inversion layer here, but the rest of this we can put a P plus region to reduce the resistance of the P well, and when we reduce the resistance of this P well, then the drop across this resistance reduces. That means the possibility of turning on this BJT is reduced, and our DVDT capability increases. Then there is a possibility of second breakdown, and that second breakdown is essentially what we described earlier in this slide. Same phenomena is happening, and basically we turn on this BJT. So, now when we turn on this BJT, you can see that the voltage that we can drop between source and drain is now defined by the what is called as common emitter breakdown voltage of this junction, which is less than approximately half of the common base breakdown of that BJT. So, what we are saying is, in BJT terms, is N plus, here is the emitter, here is the base, and here is the collector. So, that is your NPN transistor, and when we flow large amount of displacement current, which I described to you in the previous two slides, then this BJT is turned on and we go into a voltage BVCEO region. So, this transistor can now only support about half the voltage that it was capable of earlier. So, this is called the bipolar second breakdown because we have turned on the internal bipolar transistor, and as I explained to you, we can reduce this problem by reducing the resistance in the base region by heavily doping the base region. Then Of course, we have to think about the internal body diode. So, there is this PN diode here, which is shown schematically in the right hand side as an internal diode, and a lot of power electronics engineers like to use this body diode as a freewheeling diode in the device. So, there is that diode, which is the freewheeling diode, becomes important in the third quadrant operation of the device, and that diode, when turns off, then it has a reverse recovery current, which we had explained to you in the PN junction chapter, and that reverse recovery current flows through this laterally through the P well and can forward bias the BJT by the same mechanism. So, again reducing the resistance of the P well by increasing the P plus doping in the P well will help reduce this effect. So, a lot of these problems can be fixed by simply doping the bottom of the P well, which I have shown you here very heavily. Then we can basically disable the parasitic NPN BJT in the transistor, and also we can handle the reverse recovery of the body diode very easily. So, with that I would like to stop here and basically summarize by saying that we have discussed the turn on and turn off transients today, and we have shown you that there are conduction losses and there are switching losses. Conduction losses are in two parts, one during the on state, one during the off state, and similarly the switching losses are the turn on losses and the turn off losses, and they depend on the switching frequency. So, if those losses are high, then we cannot increase the switching frequency very high. And then also we talked about the ruggedness of this MOSFET, and we talked about DVDT limit of this MOSFET, which can be increased by reducing the P well resistance, and that is a very common technique which is employed both in silicon and silicon carbide MOSFETs today. So, thank you very much, and we will talk about short circuit capability of these MOSFETs next time. Thank you.